Okay, I think we'll get started. So last time in lecture 2, we derived the Gibbs-Duhan equation. We also expressed the first law in terms of only state functions. Today we're going to do something also very important, and that is to derive the auxiliary functions enthalpy, Helmholtz free energy, Gibbs free energy via Legendre transformations. So let's start with what we got last time, and that is the first law expression for total internal energy. And so we have du is TdS minus PdV plus chemical potential times change in number of moles. Now what we can do is we can identify what are called the natural variables. This is most naturally expressed as function of independent variables S, V, and N. We certainly can write U as a function of any of these variables, but the equation gets more complicated. So the natural variables are the ones which gives the most simple expression of the quantity. And so for total internal energy, it is S, V, and the number of moles that are the natural variables. Well, it turns out that we will often want in the laboratory and in calculations to have more convenient functions of different variables. And in fact, usually one of the main jobs of a thermodynamic function is to get an expression in terms of things that are easy to measure in the laboratory. So we're always wanting to switch out variables depending on what the laboratory conditions are. And let's look at, for example, S, entropy. That's difficult to control in the lab. We can't go out and purchase an entropy meter. We can't do something like that. So we might want to switch that out for its partner, temperature. Very easy to control temperature, and of course they have something called a thermometer to measure temperature. So we might want to exchange out entropy for temperature, and likewise pressure for volume. And we do so via what's called a Legendre transformation, which is really quite simple. It utilizes the property, the product rule for the differential form. Okay, so let's do it for enthalpy. So enthalpy is defined as H equal to U plus PV. So let's go ahead and just take the differential of both sides of this equation. So we have du, or dH equals du plus dPV. So let's express du via the first law. That's what's going on here. And then up to here. So here's the first law. And then here, let's express the product rule. So that's the product rule, PV. And we can see that we get a nice cancellation of our V term, and we switch out then V with P. And so if we look at our natural variables here, it's S, we still have S, but now we have switched V and P, so that's P, and then we have our N. Okay? All right, so this is enthalpy. And enthalpy is kind of an embarrassing quantity because we learn it in general chemistry as heat, and it certainly isn't heat. It's a state function, so it's definitely not heat. We can see how it is related to heat because it's the total internal energy and then accounting for some pressure volume work. But this is not work itself, right? This is not PdV, this is just PV, but this is a work-like energy. And so under the conditions that many of us first learn about enthalpy, which is in general chemistry, under the conditions of constant pressure and reversible conditions, then enthalpy reduces to heat. But it really is just this handy function, this auxiliary function. It isn't a core fundamental function like total internal energy or entropy. All right, well, let's do the same for S and T. We'll keep V and we'll switch out S and T. So we'll do that by creating the Helmholtz free energy. So the definition here, A is U minus TS. Notice a minus sign here because we've got now this is coming in as a plus dt, and this was a minus PV. So we have a minus sign here. The first bit here is, again, this is expressing du as the first law, and then minus the product state, or the product case. And we get then a cancellation of the s term leading to a dt here. So we have indeed swapped out the s and the t. And so the natural variables here are t and v and the n's, which is exactly what we wanted. Helmholtz free energy is a bit easier to intuit. This is the total energy minus this TS term. And if we look at that term, it has units of energy. Entropy has joules per Kelvin, or energy per temperature. So in SI units, that would be joules per Kelvin, times a temperature. So this is going to be an energy. What energy is that? Well, that's the energy that's tied up in making the system have entropy at a given temperature T. So the system has got to have some disorder. In order to have the disorder, there has to be some energy that's tied up in that, and that's called the entropic energy. So we're subtracting the entropic energy. That leaves anything left to be available to do work, might not do work, but available to do work. And so Helmholtz free energy is the energy available to do work. Okay. All right, let's look at Gibbs free energy. Gibbs free energy. Now we're switching out both. So this would be the last pair we have. We're going to have 4 if we're just switching out all these pairs. We usually don't switch out these. Okay, so let's go ahead and just take U and do both of what we did in the previous set there. So we're going to write this out, get everything to cancel, and we're left now with the correct natural variables, T, P, and Ni for the Gibbs free energy. Now again, Gibbs free, if we notice here, that's just the depth, that's just enthalpy. So because Gibbs free energy has enthalpy in it, it also is a little bit embarrassing when it comes to what exactly is that. But we can kind of think of it this way. This PV is sort of a PV work term. So it's the total energy accounting for any pressure volume work, and then minus the entropic energy. So you'll often hear free energy referred to as the energy available to do non-PV work or non-pressure volume work, which often is very nice because in a situation in chemistry, you might have something going on, maybe a reaction in a cell or something, and that cell then might expand, and it's doing some pressure volume work that isn't really of interest to the biochemistry. So the Gibbs free energy just completely ignores that pressure volume work under the right conditions, so under the body conditions. Okay. Let's add one more thing for today, and that's the Maxwell relations. And if you have taken an upper course in thermodynamics, so like physical chemistry, you've surely done the Maxwell relations. Now you might have forgotten them, so we'll go through this. If you remember them, then that's all we're going to do here now. Although we are going to have a little neat one pop out here at the end. So let's take our Gibbs free energy, and let's just write the differential form for it. So its variables are T, P, and N. Let's write the differential form. And this is, if you recall last time, at times I'll identify an equation as sort of math or physics. This is just purely a math expression. It doesn't matter what these variables are. This could be f, x, y, z. We would write this the same way. This is the differential form for this. Now, let's write the physics equation, which is what we just got up here, because this is deriving itself all the way back to the first law, which is a physical statement. So we have the physical statement, and we can match this up. These are independent variables, so then these are like apples, oranges, bananas. So these have to be equal, these have to be equal, these have to be equal. So you can identify each of the independent variables in the math differentially form equation and the physics auxiliary equation, and we can get a equation that relates the partial derivative to another thermodynamic variable. So there's the s, there's the minus s, there's a minus sign here, and then there's the v here. Now what we do is we crisscross our derivatives. So on this equation, I'm going to take d dp through this whole equation, and I'm going to get the second derivative of g with respect to t and then p. And then over here, I'm going to take this one, d dt, and go through this equation. So I'm going to get the second derivative of g first with p, then with t, and so that's going to give us dv dt. And then we're going to use the idea that second derivative order doesn't matter. So that's a important result from calculus. And so that means these are equal. The left-hand sides of each of these are equal, so the right-hand sides are equal. And that's how we get a Maxwell relation. So that's the steps in getting a Maxwell relation. So this is a very common one that's always done in a PChem class, but let's look at this one here. So let's pick out each of these. So let's pick out the jth one and the kth one in here. And then let's crisscross these derivatives, and we get these two equations, but these are equal. And so we have kind of this crisscrossed JK relationship here with the chemical potentials. We're not going to do too much with that, but it's kind of an interesting Maxwell relation that comes out when we add this the terms that account for the chemical energy that's going on there. All right, so these were the auxiliary functions. And so this is the most typical way that one gets these functions. What we're going to actually do towards the end of this short course is rederive these functions based on the explicit expression for u that we got in the last lecture. So that's going to be an interesting way to rethink about these auxiliary functions.